In this video, we will be covering the thermodynamics unit of AP Physics 2. We will be covering concepts such as the difference between heat and temperature, concepts of heat flow, the ideal gas law, internal energy, and how the internal energy of a system will change, and heat engines. Beginning with the difference between heat and temperature. Heat is the flow of thermal energy. Essentially, it's a measurement of the changing kinetic energy of the particles. Temperature, on the other hand, is a measurement of the kinetic energy of the particles. So heat tells you how the energy is changing in your system, whereas temperature just describes the kinetic energy of the particles. We could talk about the average kinetic energy of the particles as being equal to 3/2 Boltzmann's constant times the temperature in Kelvin. But if we're talking about a net amount of particles, a total amount of particles, we could look at the total kinetic energy by taking that amount we just calculated and multiplying it by the number of particles present. We can also use some ideal gas law and our knowledge that the Boltzmann's constant is equal to the ideal gas constant divided by Avogadro's number, and the number of particles divided by Avogadro's number is the number of moles, and we can get the total kinetic energy of a system is equal to 3/2 nRT. Temperature is typically measured using a variety of tools that all take advantage of the concept of thermal expansion. As particles move faster, they take up more space. I said that most of our temperature measuring devices take advantage of thermal expansion. Classic mercury or alcohol thermometers. You are heating up liquid mercury or liquid alcohol, and that is causing them to expand up a thermometer tube. If you're dealing with something like a thermostat or a thermocouple, you're measuring you typically have two materials that have different rates of thermal expansion. And by measuring how much one expands versus the other, let's say that this one expands more than that one, it will actually bend the materials one way or the other. That's how most thermostats in your home would work. This brings us to the concept of heat flow. The energy, the heat Q, that flows into a system is going to be equal to the opposite or negative value of the heat that flows out of another system. So in order for heat to flow in, it has to flow out from somewhere else. There are three methods through which heat is transferred. Wow, I did not spell that right. O-U. Heat can flow through conduction. If we have two objects that are in contact with one another, there can be thermal conduction between them. We could have convection. This is typically involving liquids or gases. When you have a warm surface, the gas above it will heat up through conduction, but then that gas will expand through thermal expansion and rise because it becomes less dense, transferring that heat energy up in a convection cell. or you can have radiation. A fire is a classic example of all three forms of heat flow. We have a fire here, and I put something directly in the flame. So that thing directly in the flame would heat up via conduction. If I put something over the flame, the heat rising through convection would be what heats that object. And if I hold out my hands off to the side, what I'm going to feel is the heat radiating out through radiation. The only equation we really have for this is for conduction, which measures the heat flow per unit of time. Heat flow would be measured in joules per second, so this is actually the power that the heat is flowing through, is equal to some constant times the area times the temperature difference between the two objects divided by L being the length of the conductor. So if I have a heat source and I have a heat sink, I can put a material in between them and measure the heat flow through it because I can know the length of it, I can know the cross-sectional area of it, and I know that this source is T hot and the sink is T cold. We also briefly talked about the concept of calorimetry, which is measuring this heat flow. There are a couple of equations that you should not need because they're not on the reference table, but I am going to write them. Q equals mc delta T. Q equals plus or minus mLV LF. Q equals plus or minus mLV. When you put heat into a system, it can either change the temperature if it's all one phase, or it can change phase. We use mLF if we're dealing with solid to liquid or liquid to solid. If we're dealing with liquid to gas, we use mLV. This stands for the latent heat of fusion and the latent heat of vaporization. But as long as we are in one state of matter, we would use Q equals mc delta T. If we have water that is changing phase, or any material that's changing phase, its temperature is constant because that heat is going into not changing the temperature, but rather separating out the particles and melting it, or separating out the particles and boiling it. Next topic we covered was the ideal gas law, which we learned in chemistry is PV equals nRT. Make sure that you use pressure in pascals. Make sure you use the correct unit for temperature, and make sure you use the correct R that we have on our reference table. There is a variant of this called the combined gas law, which deals with when our situation is not changing, or not our situation is not changing, but when our container is not changing the number of moles in it. We recognize that when our container is sealed, NR is going to be constant. If NR is constant, then PV over T is also going to be constant. So as long as we're not changing how many moles of material we have, the pressure times volume divided by temperature in Kelvin will be constant. We have this equation here. Be very careful when looking up references online for help with this topic, because in AP Physics 2 we have a specific definition for this law. This is one of the laws of thermodynamics. Delta U is the change in internal energy. Change in internal energy can be representing the change in kinetic energy, the change in temperature, but also it represents the bonds that are in existence between the materials, between the particles and the material, the attractive forces there. This is the heat in would be positive, heat out would be negative. And W is where this equation can be a little obnoxious. This is work. If the work is done on the system, it is positive. We are putting energy into the system. It's going to be positive work. If the system does work done by the system, it's going to be negative. So if I have a piston and I compress it, I am applying a force to change its volume. I am doing work on that piston. It would be a positive work. However, if that piston is expanding by itself, pushing something up, that would be the system doing work on the environment, and it would be negative. By that understanding, if our system is isobaric, which we'll talk about in a minute, the work done is equal to P times delta V. Where delta V is positive, means it's getting bigger. The work is negative. Because if the piston, or if the piston's getting bigger, I could put something on top of that piston, and it would be doing work to move that object. If delta V is negative, if it's getting smaller, that's because work is being done on the system. The work would be positive. And lastly, we have heat engines. We need to remember that equation. Delta U equals Q plus W. If there is a complete cycle, the change in internal energy is equal to 0. So going through an entire cycle, the internal energy would not change. However, going through a complete cycle, any work done will be equal to the area enclosed. We have PV diagrams. So let's say I start here. Certain pressure, a certain volume, and I increase the pressure, but the volume stays the same. We refer to that as isochoric, and the work done is 0 because the volume is not changing. If I then increase the pressure, increase the volume, but keep the pressure constant, we refer to that as isobaric. An isobaric process is one in which the pressure remains constant. Iso means same, baric means pressure. I would find that the work done in that process by calculating P delta V. Then we could have this process. This is another isochoric process. And then here we have another isobaric process. This second isobaric process is going backwards, so we would actually be subtracting that volume. So to find the total work done by this process, we would calculate this volume here and subtract off this volume here. There are two other kinds of processes. We could have isothermal or adiabatic. They're hard to tell the difference between. The easiest way to tell the difference between isothermal and adiabatic is isothermal means same temperature. And if we remember PV over T equals PV over T, if the temperature is the same, the denominator will cancel out. And we get P1 V1 equals P2 V2. So if I could measure this pressure and this volume and multiply them together, and then measure this pressure and this volume and multiply them together, they should be constant if it is truly isothermal. Because isothermal means same temperature, the change in internal energy for an isothermal process is equal to 0, which means that Q equals negative W. So any work being done is being done because there is heat flow. On the other hand, we have adiabatic, which is when the heat is not allowed to flow. So any work being done is changing the internal energy of the system. And that's going to do it for this review of the fluids unit of AP Physics 2.